Good morning, students. Audio video is okay. Anyone, please reply. Audio
Yes,
video
sir.
is okay.
Yes, sir.
Yes, thank you. Thank you. So, last time we have started the standard distribution. So, we have covered Bernoulli distribution, binomial distribution, geometric distribution, and the Pascal distribution. Now, next is Poisson distribution. So, Poisson distribution from application point of view in discrete random variable is very important. So Poisson distribution here when we say x is a Poisson variate, right? If we say x is the Poisson variate, so it measure number of successes. It count the number of successes. Only here the number of successes are important. For that, how many Bernoulli trials required, that is not so important. Only when we are conducting the Bernoulli trial, at that time we have to count how many successes we have. So it is also a discrete random variable. So x follow the Poisson distribution, right, with parameter lambda. Here lambda is the governing parameter. So it's PPF, point probability function or probability mass function, because it is a discrete. So we call it as a point probability function or probability mass function. It is given by e to power minus lambda, lambda to power x upon factorial x, where x can take the value 0, 1, 2, 3, and so on. Means x can take 0 success, 1 success, 2 success, or many more success. And for this, ex is means mean of the Poisson distribution is equal to lambda, and variance for Poisson variate is also lambda. So this is the distribution for which mean and variance are equal, and its movement generating function, we can write it as a e to power lambda into e to power t minus 1. And this ppf has the maximum value when x is equal to greatest integer of the lambda. Means when we have the x, right, and here we have the fx, or here you write lambda. So its maximum value lie at the greatest integer of the, because it is a discrete, so only we have the point, right? So greatest integer of the lambda. If lambda is the positive integer, say k, then ppf has the maximum at the two value, at x is equal to k minus 1 and at x is equal to k. At that time we have the maximum value at the 2 point, and here we have the x k minus 1, and here we have the x is equal to k. So in this case, we have the maximum value at the 2 points. Now, as I have told you, in this the x measure the number of successes, right? For that purpose, whatever the number of Bernoulli trials, repeat we can repeat. But in the binomial we have the in number of successes in n Bernoulli trials. In binomial distribution we have number of successes in n Bernoulli trial. So in this case we are taking the n tends to infinity. So it means the Poisson distribution is nothing. It is the limiting case of the binomial distribution. Means in this case, in we have the binomial distribution with parameter n and p. So n, if you take the n as a very large, infinite, and probability of the success is very rare, right? So this tends to 0. Here the n tends to infinity and p tends to 0. That is the rare event. That is a rare event. And here we have the large number of trials, large number of Bernoulli trials. Then the binomial distribution limited to the tends to the Poisson distribution with parameter lambda, where lambda is moderate value, where lambda is moderate value, and it is equal to n into p. So here it is written limit n tends to infinity, p tends to 0, and np tends to lambda. The binomial variate tends to the Poisson variate. Poisson variate, and here you can see for the binomial distribution. For the binomial distribution, Ex is what? It is the NP, and for the Poisson distribution, Ex is what? Ex is equal to lambda. That's why lambda is equal to NP. We are taking, means we are taking that in both cases number of the successes on an average number of successes are equal. So Poisson distribution is nothing, it is the limiting case of the binomial distribution. Now, most important property of the Poisson distribution for which it has the means various application, that is the additive property of the Poisson distribution. So if x1, x2, xn follow are the independent Poisson variate with parameter lambda 1, lambda 2, lambda n respectively, means it is given to you that xi follow the Poisson distribution with parameter lambda I. Then respectively, right, let you define the another random variable x, that is the sum of the Poisson variate. Sum of Poisson variate means x1 plus x2 plus xn. Then then this random variable follow which distribution? That is the additive property of the Poisson distribution. So this x follow the, then x will have Poisson distribution with parameter lambda, where lambda is equal to summation of the lambda I. Summation of lambda I. So we know that mxt is what? It is the expectation of e to power tx. It is the expectation of e to power tx, and x is what? X is the e to power t, and x is what? It is the x1 plus x2 plus xn. That can be written as e to power t, right? T x1, e to power t x2, and e to power t xn. That is the m of x1 t, m of x2 t, and m of xn t. And for the Poisson distribution, you know what is the moment generating function. So e to power minus lambda e to power minus t e to power t minus 1, right? So not minus, it is the plus, right? In e to power lambda 2, e to power t minus 1, and e to power lambda n into e to power t minus 1. So here we have this. So if you take the e to power t minus 1 common, so we can write it as a e to power lambda 1 plus lambda 2 plus lambda n, and e to power minus e to power t minus 1. That can be written as e to power lambda into e to power t minus 1, where lambda is equal to lambda 1 plus lambda 2 plus lambda n. So from this, as I have told you, moment generating function is what? It is the fingerprint. It is a fingerprint of the distribution. So by seeing the expression of the moment generating function, you can judge that x follow the Poisson distribution, because it has the same expression, whatever the expression of the Poisson distribution. So from here we can say that the sum of the Poisson variate also follow the Poisson distribution. Sum of Bernoulli distribution follow the binomial distribution, right? That we have seen. Sum of the geometric distribution follow the Pascal distribution, right? So these things we have seen. So we have covered the discrete random variable. Now we are moving to the continuous random variable. So in the continuous random variable, first we will study the gamma family or exponential family. In that we have the first distribution, exponential distribution. So here the exponential distribution, x means here we say x is what? X is the exponential variate, exponential variate, and it measure the time to the first occurrence, time to the first occurrence, right? Means if it is the time scale, at this time we there is any occurrence, so it is the time it is the time for the occurrence of the first event, right? We can have the occurrence at this point, so we have the, right, we can have the occurrence at any moment, so that is the random. And that random, and it is what? It is the continuous random variable. That occurrence time will be the random, and it is a continuous random variable, right? So here we say if the x follow the exponential distribution with parameter lambda, means here the lambda is what? Governing parameter. So its PDF, now it is a continuous distribution, so we say the PDF means probability density function. So PDF fx lambda is given by the lambda e to power minus lambda x, right, where x greater than 0 or 0 elsewhere. It can be represented as 1 upon beta e to power minus x upon beta for x greater than 0 is equal to 0. Means from here we can judge that lambda is equal to 1 upon beta, and fx will become, fx will be the 1 minus e to power minus lambda x. We are not going in the derivation part because you have already learned all these things, how to derive the capital fx. So only main thing is to brush up here all the basic distributions so that we can directly use. And corresponding mean is equal to 1 upon lambda, and variance is equal to 1 upon lambda square. So if the variance is 1 upon lambda square, so you can say that standard deviation is the positive root of variance, so it is the 1 upon lambda. So here you can judge that for the exponential distribution, standard deviation and mean are equal. For the exponential distribution, mean and standard deviation are equal, 1 upon lambda, 1 upon lambda, right? If you're writing the PDF in terms of the beta, then ex is equal to beta, and variance of x is equal to beta square. So here the most important thing is to recognize what is the meaning of the beta and what is the meaning of the lambda. Here the beta is nothing, it is the mean time. Mean time means average time required for occurrence of any event. Means if I am saying that on an average every students are coming after, means the first student is coming after the, means after the 1 minute or 2 minutes, so that is the average time, right? That is the average time, right? Mean time. And here lambda is what? It is the 1 upon beta. So 1 upon beta represent the mean rate. It is very important to understand the difference between the lambda and beta. So here the lambda is nothing, it is the mean rate. Mean rate means in a unit time how many students are coming in the class, that is the mean rate. Means in a unit time how many events are occurring. Here if the events are occurring randomly, right, randomly, so in the 1 hour, in 1 hour or unit time, in the 1 hour how many, on an average how many events are occurring, that count the, that count or that give the mean rate, right? Means mean number of occurrences, mean number of mean number of occurrences of events in unit time, in unit time. So that represent the mean rate, and its reciprocal will be the mean time. Is there any doubt to understand the mean rate or mean time? If you have to ask the question, you can open your mic. If you have any doubt, please ask for the exponential distribution. So I believe there is no doubt. And for the exponential distribution, we have the most important property to make it an important distribution. So here the memoryless property, the only in continuous distribution, only the exponential distribution follow the memoryless property. And in case of the geometric distribution, in case of the discrete distribution, geometric distribution also follow the memoryless property. Means for the discrete random variable, only the geometric distribution follow the memoryless property, and in case of the continuous random variable, only the exponential distribution follow the memoryless property. So what is the memoryless property? Right, memoryless property is that, means the the future event, the time of the future event depend only on the current event. Right, means it forget the past events, it forget the past events. Means for example, if we when there is a queue, so we are interested how many person are present in the queue. Right, who has taken the services from us, that is not important. So we forget the past. Right, when we are in the queue, so we are interested how many people are present in front of me, who has taken the services, that is not important for me. So that kind of the things are memoryless. Right, means we forget the past events, we forget the past event, we only care for the current events. So that is the property of the exponential distribution only in continuous. So mathematically, it can be written as probability of x less than equal to x naught plus x, given that x greater than x naught is equal to probability x less than equal to x. Means if we have, so if we have the timeline, right, so I'm saying that the time x naught has elapsed, the time x naught has elapsed. Now it is asking what is the probability that up to the time x any event is occurring. So here x greater than equal to greater than equal to x naught plus x, right, or less than equal to x naught plus x, means up to the time x there must be occurrence of the event. So its probability is equal to x less than x, means it forget what has happened in this period, whether there is occurrence non-occurrence, that is not important. If this time elapsed, so it elapsed, so it elapsed, right, we have not to take care. Only we are interested for the remaining time, only we are interested for the remaining time. That is the memoryless property. So in so here, that is written here, probability x less than equal to x naught plus x, given x greater than x naught, it is the random variable, x greater than x naught.
Sir,
So it is in yes, please speak little louder.
sir, can you just for once show the one note again? Yes, sir. In this
Hmm.
case, you have written x less than x naught plus x. So
Hmm.
x naught is X naught will be taken twice, na? In X also it is
No, no,
X naught
it is
plus
just
1.
representation. It is just representation. It is representing that this period only. That is not mathematical things. Only it is representing that it crossed the X.
X naught plus X, what
Ha,
does it
X naught
mean?
plus X, right? X naught plus X means this period is the X. This period is X.
Okay, okay. Okay, sir.
This period is X. So this time is not of our consideration. That is the forgetlessness. We forget this period. Whatever the time elapsed, that elapsed for us.
Okay, sir.
Means either the thing is either you compute the probability for the complete time or you compute the probability for the remaining time. Both will give the same result. This time we have not to take care. Clear? So here we have, so here what we have to compute? We have to compute that probability x less than equal to x naught plus x given x elapsed the x naught. So it is the probability of A given B. We know that it is equal to probability of A intersection B divided by the probability of B. So x less than x naught plus x intersection x greater than x naught divided by the probability of x greater than x naught. So it is the timeline x naught x. So uh, x greater than x naught, x greater than x naught, and x less than x naught plus x. It means where we have the x, where we have the x, probability x lie between x naught to x naught plus x divided by probability x greater than x naught. And from the property of the probability, we know that it is the f of x naught plus x minus f of x naught divided by 1 minus f of x naught. And we know that what is the f for the exponential distribution? E to power minus lambda x, 1 minus e to power minus lambda x. So 1 minus e to power minus lambda into x naught plus x minus 1 minus e to power minus lambda x naught. Lambda x naught divided by 1 minus e to power minus lambda x naught. So that will give you 1 minus 1, 1 minus 1, and it will give you e to power minus lambda x naught minus e to power minus lambda x naught e to power minus lambda x upon e to power minus lambda x naught. So in the numerator, if you take the right in the numerator, if you take the e to power minus lambda x naught common, and from the denominator you if you cancel, so 1 minus e to power minus lambda x. So what it represent? Right? So it is the probability x greater than the or x less than equal to probability x less than equal to x. Right? It is the CDF of the exponential distribution. So here you can see it is the independent of x naught. That is the forgetness. That's why it is termed as the memoryless. So memoryless forgetfulness, right? Or most important name is the Markovian. It is the Markov property. Markov property of the exponential distribution, right? It is given by the Markov, mathematician Markov. That's why it is known as the Markovian property. Now, if events are occurring through the Poisson process with parameter lambda, then the inter-occurrence time will have exponential distribution with the same parameter lambda. Means here what is the important thing? Here events are occurring randomly. Events are occurring randomly, right? So if events are what is the Poisson distribution? Number of occurrences in a over the continuous time, over the continuous time, means there we define for the time, but it is true for any continuous thing, continuous length, continuous area, continuous space. For example, if we have to count in particular room number of bacteria in room, so that is the Poisson process, right? Poisson process measure the number of the successes in a over the continuous scale, whether the time, length, area, space, anything, but it should be on continuous. So here, if you say the occurrences are means here, let's say the time t. So xt means xt count number of occurrences in interval 0 to t. So here the number of occurrences means count count of the event. So it follow the Poisson distribution with parameter lambda, if it is given to you, then interoccurrence time, the interoccurrence time interoccurrence time interoccurrence time interoccurrence time interoccurrence time interoccurrence time, right? This interoccurrence time follow the interoccurrence time interoccurrence time follow the exponential distribution with same parameter lambda. So that is the relation between the Poisson distribution and exponential distribution. If interoccurrence time follow the exponential distribution with parameter lambda, then the number of occurrences in a unit time follow the Poisson distribution. So here you have seen lambda is what? It is the mean rate of what? Rate of occurrences occurrences, right? Mean rate of the occurrences in exponential distribution, and that is the same thing, right? That is nothing, that is the expectation of the Poisson variate also. Lambda is the mean of the Poisson variate also, means in both, whether the exponential distribution or the Poisson distribution, we have the same mean rate. In actual, exponential distribution is the continuous random variable and Poisson distribution is the discrete random variable. Events are happening in discrete over the continuous time. So interoccurrence time follow the exponential distribution if occurrences follow the Poisson distribution, or if the occurrences follow the Poisson distribution, then interoccurrence time follow the exponential distribution with the same parameter lambda, where lambda is the mean rate of occurrences. So these theorems make make the exponential distribution as the most important distribution from the application point of view. So this is the first distribution from the gamma family or the exponential family. Now next is the gamma distribution. So for the gamma distribution, we must have the idea what is the gamma function? Gamma function be represented by the capital gamma, and gamma of p is nothing, it is the integral 0 to infinity x to power p minus 1 e to power minus x dx for p positive, right? And gamma p is equal to p minus 1 gamma of p minus 1, and gamma of 1 is equal to 1 gamma, if n is integer, if n is the positive integer, then gamma of n is equal to factorial of n minus 1, and gamma of the half is equal to root pi. So these things you must know about the gamma function, basic things about the gamma function. So from here we can define the gamma distribution. So gamma distribution, here the x, time to occurrence of the r events. So in this case, what is happening? Here we have the occurrences at the random period, occurrences at the random period. Let's say we have the r occurrences, right? We have r occurrences. Here we are taking the r as a 4. So we have the r occurrences. So inter occurrence of r, in inter occurrence time of the r consecutive occurrences follow the gamma distribution. The time required for the occurrence of the r events follow the gamma distribution. So here, x measure the time to occurrence of the r events. Let x follow the gamma distribution with parameter r and lambda, where again r is what? Number of occurrences, r occurrences, number of occurrences, and lambda is the mean rate of occurrences. Lambda is mean rate of occurrences. Mean rate of occurrences. Mean rate of occurrences. Then its PDF, because it is a continuous time, right? It is a continuous time. So PDF is what? PDF is with parameter r and lambda as lambda into lambda x to power r minus 1 e to power minus lambda x upon gamma of r for the x positive, right, greater than 0. And its ex is given by the r upon lambda, vx is variance of x is given by the r upon lambda square, and mxt is given by the lambda upon lambda minus t to power r, right? So in this case, one important fact you can observe, anyone can tell what is the important fact you can observe? Anyone, please try. By seeing the expression, anyone can guess.
If r is
From this
equals to
diagram,
1,
anything you can guess. Okay, I am giving you a hint. First, recall the exponential variate. What is the exponential variate? First,
if r
think
is
about
equals to 1,
no, that is the r is equal to 1, but that is another thing. What is the exponential variate? Time required for the first occurrence. 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 Now you can say something. Yes, anything now? X is what? X1, X2, X3, X4 means X, it is the X1 plus, X2 plus, X3 plus, X4. So this is what? This is the gamma variate. These are what? Exponential variate. Now, you can try. Now you can try. X is what? X is the means the sum of exponential distribution. Sum of are independent exponential variate is gamma variate. Is gamma variate. Clear? Is the gamma variate. Sum of R independent exponential variate is equal to the gamma variate. So if you have to compute the EX, so what we have? E of x1 plus x2 plus xr. So and we know that exponential means expectation follow the linear property. So it is the E of x1 plus E of x2 plus E of xr. E of xr. So and what is the mean of the exponential distribution? 1 upon lambda, 1 upon lambda, 1 upon lambda r times. So it will give you r upon lambda. The same whatever we have for the gamma distribution. Similarly, if you have to compute the variance of x, so we have the variance of x1 plus x2 plus xr. So it will be the variance of x1 plus variance of x2 plus variance of xr. So this will give you 1 upon lambda square because xi follow the exponential distribution. So lambda square 1 upon lambda square. So it will give you r upon lambda square. R upon lambda square. Clear? Similarly, if you have to compute the mxt, we know that it is the expectation of e to power tx and e to power t into x1 plus x2 plus xr. That can be written as e to power t x1, right, plus e to t x2 t xr, which can be written as e to power t x1 e to power t x2 e to power t xr. That is the moment generating function for the x1, moment generating function for the x2, and moment generating function for the xr. And we know that for the exponential distribution, lambda upon lambda minus t, lambda upon lambda minus t, and lambda upon lambda minus t, right? So this will become lambda upon lambda minus t to power r. The same thing we have written here. Clear this part? So from here, that's why these two distribution belongs to the either you say exponential family or the gamma family. So if r is equal to 1, then gamma variate reduced to the exponential variate, means a time required for the first event. So exponential distribution is nothing, it is a particular case of the gamma distribution. Now if xi, that whatever the theorem I have told you, that is written here. If xi follow the exponential distribution with parameter lambda and independent, all xi are independent, then x is equal to sum of exponential distribution, right, I from 1 to n of xi follow the gamma distribution with parameter n and lambda. That I have told you, right? If xi follow the gamma distribution, if xi follow the gamma distribution with parameter ri and lambda and independent, then x is equal to summation xi, means sum of gamma distribution, that represent the sum of, it represent the sum of gamma variate, sum of gamma variate. So sum of gamma variate also follow the gamma distribution with parameters summation ri comma lambda. So that you can judge from the diagram. If I'm saying that, right, here we have the occurrences, here we have the occurrences randomly, and if you say the first few occurrences occur follow the exponent distribution, x2 distribution, x3 distribution. So the total follow the sum of the x1 plus x2 plus x3. If this follow the gamma distribution with parameter r1 and lambda, this follow the gamma distribution with parameter r2 and lambda, and this follow the gamma distribution with r3 and lambda, where r1, r2, r3 represent number of events required, right, and lambda is the mean number of occurrences. So for all we have the same mean number of occurrences, then time required for occurrences of r1 plus r2 plus r3 with mean number of occurrences lambda also follow the gamma distribution. Clear? Then after, this is also from the gamma family, but it has the means now most important thing, just I'm revising few things. Now please pay attention, right? We have studied the few discrete distribution and few continuous distribution. So let's say events are occurring. Uh, Means if I say which brand you prefer in mobile, anyone please tell. Let's say Apple. So if I say Apple, if I ask from the Bhuvan Gupta whether you have the Apple or not, he can answer yes, I have the Apple. Then I ask Ria Shekhawat whether you have the Apple or not. Then she replied no. Right. So if I have the interest, right, if I have the interest in the answer yes or no, if I ask from the Shreya Misra and she said no, then I ask the Pushpendra, then he says yes. So if we have such kind of the question, right, then we say it is the Bernoulli distribution. Now if I am interested, if I ask, right, if I ask from the many students and they are answering in this way, right, whether they have all are independent to each other, right, all are independent to each other. Now if I say, if I am interested, right, out of the five students out of the five students out of the five students out of the five students, right, how many have the uh, Apple mobile? So here the answer is 2, here the answer is 1, here the answer is 3, random. If we have such situation, then we apply the binomial distribution. If I am interested for getting the first Apple mobile with means from how many students I have to ask, if I am interested in that. So here the x is equal to 1, here the x is equal to 3, here the x is equal to 4, means one student, two student, three student, fourth student, right? Then here we have the x is equal to 2, no, 3, x is equal to 3, here the x is equal to 1, right? This is the 3, this is the 1, this is the 2, 1, 1, right? Here we have the 4, here we have to count 3, and here we have the 1. That is the random, and means number of students required for getting the first Apple mobile. That is the geometric distribution. If I am interested from how many students I have to ask for the three Apple mobiles. Three Apple mobile means one, right? If I count 1, 2, 3, 4, 5, 6, 7, 8. So here we have the x is equal to 8 for the three mobiles. Then 1, 2, 3, 4, 5, 6, 7. Then we have the x is equal to 7. Means from the 7 students, I have to ask for getting the three Apple mobiles. So it is nothing, that is the Pascal distribution, right? That is the Pascal distribution. So I'm telling you the situation. I'm telling you the situation when you have to use the bridge distribution. Now, now, if you are sitting in the class, right? If you are sitting in the class, and this is the first row, right? This is the first row. This is the first row. This is the second row, right? This is the third row, and this is the fourth row. Now, I'm saying that this row is continuous. This row is continuous. This row is continuous. In this, if I am interested in over the continuous time, or over the continuous row, over the continuous line, right? Over the continuous space, how many students? How many students have the Apple mobile? Let's say he has the Apple mobile. He or she has the Apple mobile, right? He has the Apple mobile, or he has the Apple mobile. So here the x is equal to 1, here the x is equal to 2, here the x is equal to 1, right? Let's say here the x is equal to 3. So this is nothing, this is the Poisson distribution. Number of successes over the continuous line, over the continuous space, over the continuous time, right? That is the Poisson distribution. Now, how many distances, right? How much distance I have to cover, right? How much distance I have to cover for getting the first student who has the mobile? So that is the first distance. That is the first distance. That is the 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 distance. Means if I started my journey from my department, and I'm asking from each student Bernoulli trials, whether you have the Apple mobile or not. So how many distance I have to cover for for the first Apple mobile? That follow the exponential distribution. And for the three mobiles, then that follow the gamma distribution, right? Means how many distance I have to cover for getting the three Apple mobiles, that follow the gamma distribution. And how many distance I have to cover, right? How much distance I have to cover, right? That is the exponential distribution, right? For the first event, exponential distribution. For the R events, gamma distribution. Clear? It is very important to understand the situation when we have to use the
Sir,
bridge distribution. Yes.
sir, so it doesn't matter how many failures are there in between. Like for example, success of three Apple mobiles.
Huh?
So in between these two, if there are people who
Huh, there is no, that is not a, that's why na memoryless. We are interested only for the success in case of the
okay,
exponential.
okay, sir, yeah,
So whatever the number of the failure it may be, whatever the number of failure it may be, whatever the number of failure it may be,
okay, sir.
only we are interested for the success. That's why we are saying na, we are counting the rare event over the continuous time in the Poisson process.
Yes, sir. Okay, okay.
Number of bacteria in the room. So room is very large, continuous space, three-dimensional space. In that we are counting the bacteria, right? From one corner to another corner. So it is very rare event.
Yes, sir. Understood.
For example, presently we have the corona patients. So let's say this is any Rajasthan state. So in one district we have to measure, in another district we have to measure, in a third district we have to measure. So that area is the continuous. In that, count is the discrete. Count, corona patient is the discrete. That we have to count. So accordingly, we have to decide which distribution we have to apply. So chi-square distribution we continue in next class. Anything you want to ask about the distribution, because it is very important. Accordingly, according to situation, we have to use this. So it is very important to understand the situation. So if you haven't doubt, you may leave.